LU decomposition, if we use SciPy linear algebra.lu, okay, of B, permute L equal to false, it return V this. It don't do permutation, it don't do row switching. The answer is a tuple, so I have 3 numbers to receive the answer, PLU, okay, equal to SP linear algebra.lu. And it gives me P, it gives me L, and it gives me U. So the diagonal term of L is 1. Okay?
I have a question.
Yes.
You have NP seal on that one, and on the previous code you have NP floor, like num5.4. So what's the difference between?
Point 1, if you do ceiling, you get 1. Point 1, if you do floor, you get 0. Okay? Ceiling is just round up. Floor, round down. For decimal point. So point 1, if you ceiling of point 1, you get 1. Ceiling of point 1, of floor of point 1, you get 0. So the reason that I do that is just to like make matrix. So that I don't have to type.
Can you explain this again?
Each thing one by one. You see this code, this 2 line of code?
Yeah.
That is just to generate a random number matrix. Just that.
But what about the seal? The seal, what does it do?
Oh, you type it yourself.
Yeah.
If you random typically generate the number between 0 and 1. So number between 0 and 1 is not 1, 2, 3, it's 0 and 1. I multiply by 10, then it become what? 0 to 9 or 0 to 10. So, but I don't want 0. If it is less than 1, I want it to be 1. So I use seal. Just that. So PLU is to do LU decomposition. And okay, once I do LU decomposition, see this part I try it step by step, but you don't have to worry about it. The whole code is here. This is like doing LU decomposition. I explained it to you earlier, right? That we have the formula. We just use the formula. We do LU decomposition. Just that. How do you know? How does it work? You extract each part of the code and run it by yourself. You get my point? In homework. And then you will find out how does it work. Okay? Just talking about it all day long doesn't help much until you're actually doing it. Okay? So we have the formula. We have formula for loop L part, U part. We put them together. That is the formula. So in each step, we finish L and then we finish U. Okay? So we have LU decomposition. So basically, just put the formula that we already have inside. You got it? Earlier we had the formula, right? We just put in the code form. To put in the code form, one thing that you have to be careful is the output. Is it going to be NumPy array? If so, what is the dimension? Is it a vector? Is it a vertical column? Horizontal one? You have to check. Okay? Alright. Try U. np.try U. So that make I have input matrix A, which is okay. Input matrix B, 15 something something something. That's my input, right? If I want just top triangle, 15 and 14, I use this function np.try_u, triangle, upper triangle. So basically, it replaces everything with 0 on the bottom left. Okay. And try L, this means it replace everything on the top part with 0. That is try L and try U. And if I want to put the diagonal term to be 1, I just do this. This is because this function of my method, when I do everything, it doesn't create matrix L and matrix U separately. It combined together with the understanding that everything just replaced with A. So when you input matrix A in, the output that you get will be matrix A, but this time upper triangle will be matrix U. Lower triangle will be matrix L, excluding the diagonal term that is 1. So after I know the answer is matrix A, right? Answer is matrix A. So I have to retrieve the U value. To retrieve the U value, I say, okay, NP try U A. It put matrix A and it replaces everything on the bottom left to be 0. So this time it replaces everything on the top right to be 0, and NP dot diag indices 4 equal to 1. So this means, okay, in the bracket, that's the index for the diagonal term. It's 1, 1, 2, 2, 3, 3, 4, 4, 5. Oh, 0, 0, 1, 1, 2, 2, and 3, 3. That's the index. Okay. So I say L on those locations equal to 1, so equivalent to make the diagonal term to be 1. Just that. I have code one part at a time. I check the answer. Okay, left hand side equal to right hand side. Now with partial pivoting, we do switch row and column. Okay. So P equal to P transpose, P times P transpose equal to identity matrix. So all this is just to tell you that we have to track P. We need to know how many times that we do row switching. Why is that? Why do I care about how many times that I switch the row? That is going to impact on
Conditional complexity.
Determinant. For determinant, you remember the formula is x minus 1 raised to the power of s. So once we get L and U, we can do Ly equal to C, solve for y, and then do Ux equal to y, right? But this time we don't have just L and U, we have PAX. We have P, right? We multiply P with A first. We do the switching before LU decomposition. So I have PA x equal to LU x equal to P D. So when we switching the left side, we also have to switch the right side. You remember in the Gaussian elimination, you switch both sides of the equation, right? So this time, we multiply P on both sides. So we multiply P with AX and P with D. So what is that? So we say, okay, solving for y and c are column vector. Y is UX, C is PD. So this whole thing is C. Okay. And we have LU. So LUX. UX is a new variable. So UX is Y. We have L multiplied by UX, which is Y, equal to P multiplied by D. Okay. So this way you do forward substitution with PD and UX. Okay. So we have Ly equal to C, but this time our C is not just matrix D, but it's P times D. And our Y is U times X. Get my point? So once you get Y, that is UX, then you do UX equal to Y, then you can solve for X, right? Use backward substitution. So basically we have PA equal to LU. So this time PA equal to LU. And you need, when I multiply P transpose LU, A equal to P transpose LU because P transpose equal to P inverse. You see this one over here. So if I have P inverse multiply over here, so we will get A equal to P transpose LU. So basically everything is the same, except instead of D, you have P multiplied by D. Good? The step for LU, everything is the same. So this is SciPy. Okay, this one is permutation is false. And this is manual method. Okay. This time you may see that, hey, I have this line, which is find the maximum, and I have this line. This line is, instead of 2 lines, I have 4 lines. Okay. First, I search to do the permutation. First, I search for the maximum index, and then I check, hey, if the row that I am at is not having the maximum index, then we switch. Otherwise, we don't switch. When we switch, we don't just switch matrix A, but we switch matrix B too, matrix P too. So originally matrix P is identity matrix. So this way we know how many times we switch, okay? Or we know like how matrix P look like. So P dot PNS, we get diagonal matrix. After I know my permutation matrix, what do? You see, this line changed a little bit. So instead of A equal to B, I have A equal to P multiplied by B. Okay. So I multiply with the permutation matrix first. So that's how I get PA equal to UX, right? This time you have PA equal to UX. You don't do LU. You don't do LU decomposition of matrix A, but you do LU decomposition after you do partial pivoting, after row switching. So you do row switching first. Once you finish row switching, then you can do LU. So the step for LU is the same. We have loop for L and loop for U. And after that, we get upper part, lower part. Same thing. Then we have forward substitution. Forward substitution is similar to backward substitution, but this time we just move forward. So when we put everything together, I write PLU, take the input of B, okay, and then we split it. So first step, I create matrix P as an identity matrix. So this time it's not just LU decomposition, it's PLU, have permutation matrix, so that it works when you have 0 on the diagonal term. So first step, I do partial pivoting. Pivoting just switching row. When I switch the row of A, I also switch the row of P, right? So that I know how switching occurs. Then I do LU decomposition. As usual, where's my LU decomposition? Okay. Loop for L and loop for U. This one is done as usual, right? Okay. Then I get my upper, my lower, and then I'm done. So I get PLU. I didn't get the answer yet. To get the answer, I have to do forward substitution and backward substitution. So my PLU just split it, right? Solve LU means get PLU from my previous function. And this time I do forward substitution and then do backward substitution. And then I'm done. For forward substitution, one thing that you need to know is you see this one? P dot dot D. So when you do forward substitution, it's not forward substitution with D. It's with P multiplied by D. Just that, and then it's done. Okay? Good? So this way, we do row switching, and we know how to use row switching when we do forward and backward substitution. So you multiply P with D, that is C, and then we do forward substitution, and then we do backward substitution, get the answer. So x equal to solve LU BD. So I try to create my own function that's similar to what you have in SciPy and NumPy, right? It's just that. So when I do this, I solve it. B dot x equal to that. What about matrix D? Hey, it's the same. So this means left hand side equal to right hand side. So my answer is correct. Good. So LU decomposition and Gaussian elimination is they are equally slow. Okay? LU is better in some cases. Daniel, what's that? When will it be better to use LU?
Oh, probably when you have the problem of diagonal matrix being zero.
Huh?
When you have the diagonal matrix being zero.
We can do pivoting with Gaussian elimination too. So wrong answer. You want to try more? Or who do you want to try? Who do you want to help you?
Okay, I would say when the matrix is really large.
Gaussian and LU decomposition, if matrix is very large, both of them same speed, slow.
Okay.
In what cases that LU is going to be better than Gaussian elimination? Because they are the same. They are basically the same. But in some cases, it's better. What is that case?
Sparse matrix.
No. Who do you want to try? If not you, point the finger and I will ask that person.
Why would me?
Me. Okay. Gaussian elimination and LU decomposition, they are both slow. In some cases, you prefer LU. What are those cases?
I don't know. I guess LU converges better than Gaussian.
I disagree. Okay, who do you want to help you?
Everyone can help me.
Point the finger.
Maybe none. Yeah.
None.
I'm going to point to you.
In the case where you have repetition, so and you have just change in B. If you have AX equal to B, AX equal to C, AX equal to B1, AX equal to B2, AX equal to B3, B4, B5, B6. If you use LU, you decompose A just once. And the rest, you just do forward substitution, backward substitution, which is just 2 nested for loop. If you do LU is 3 nested for loop. When I wrote it, it may seem like it's 2 nested for loop, but it's not. Look at LU. We see for loop I, for loop J. Why do I say that is 3 nested for loop? Okay. Do I do okay, for loop I go to 1 to n, then do for j go to 1 to I minus 1, sum, and then have k. Or have ijk. So that's 3 nested loop, right? For forward and backward substitution, it's just 2. nested for loop. So this means if you have same A, if you have many equations with the same A but different B, if you have 1,000 equations, LU decomposition, you do decomposition just once, and the rest you do just forward and backward substitution. But if you use Gaussian elimination, then you have to do that elimination kind of 1,000 times. Okay? To use SciPy LU decomposition, you have PLU, P, L, U equal to SciPy dot link ANG linear algebra dot LU. Let's do LU decomposition, but didn't solve it. It just decompose. Okay. So LU equal to LU factor. It put L and U in the same array. Okay. If you want to solve it, you do LU solve LU comma B. So this LU is the matrix that is already decomposed. Okay. So if you want to do LU decomposition with SciPy, step 1, do factorization. Decompose it into two matrices, into PLU first. See, LU factor. So this LU factor gives you L and U. So length of that matrix is 2. So, okay, and it store the information in the concise way. So once you factorize it, then you can solve it. This method, it doesn't do 3 nested for loop, it just do forward and backward substitution. So if you decompose just once, you can reuse it 1,000 times. Okay. All right. NumPy.set underscore print option just tell you you want to set how many precision digits. So if you want less digit, this is how you do it. Answer from me and SciPy, they are the same. So that's how you can trust user program. Okay, we check. Even me, I can make mistake, and I actually make mistake every time that I do the code. So I have to check. When you start, do with something that you know solution first, so that if you have bug, you put the solution in, then you can find where's the bug. Like last time that I do with Excel, I cannot find the bug early on. The way that I find the bug for that method is Jacobi, right? I find the bug by put the answer in, and if it doesn't give me something right, then I know where's the bug. You see my point? So start with something that we have answer. Speed test. You can do this by yourself. I test the speed, okay? So first I do LU factor and then LU solve. It takes 47 microseconds. Solve LU, my method take 10 times slower. Okay, so use SciPy. But what if I ask you to count how many times that the calculation occur? Then you have to put your counter in the most inner loop to actually count. You cannot do that with SciPy, can you? No. So you may have to use my code and just put it in the right place. So for L and U, they are in the same level of for loop, right? They are 3 nested for loop twice. So you put your counter into location for L and U, and then you can count how many times that calculation occur. So I want you to, in the homework that you will get soon, compare what is the difference between LU decomposition and Gaussian elimination. What is how many times that multiplication, addition, subtraction, or division occur in each? You can count, right? So if you want to count how many operations, what do?
Put a counter.
You put a counter there and then you multiply by, you actually count it. Like, okay, for each equation, what happens? So you have multiplication one time and addition one time. That 2. Okay, let's not count assignment. So you have 2 operations. So whatever counter you put over here, you multiply by 2. That is the total number of operations, right? We should compare Gaussian elimination and algebraic composition. Which one has how many operations? Okay. We don't worry about the speed, but we want to actually, because faster computer do the job faster. If it use multiple threads, it become faster. But I worry about the algorithm itself. Algorithm itself, which one is faster, or they are the same, or how many times you can actually count, right? Determinant. It is odd that you can just do root of linear equation but cannot calculate determinant. You should be able to calculate determinant. Why? Because it's just minus 1 to the power of s multiplied by pi Lii and pi Uii. Pi Lii equal to what? Come on. Pi Lii. Multiplication of the diagonal term of lower triangular matrix equal to 1. 1. You agree? Joe, you agree? Okay. Because for matrix L, we put 1 in the diagonal term, right? Okay. So determinant is just minus 1 to the power of s multiplied by multiplication of diagonal term of the matrix U. If you do just Gaussian elimination, what you get is matrix U, right? And you don't have any switching. Let's say you don't have any switching. So this means you have just diagonal term after the Gaussian elimination, multiply them together, then you get the determinant. Correct? If you don't have switching. If you have switching, you have minus 1 to the power of s. S is the number of times that you do switching. How do we know s? One easy way.
I don't get it. Okay, can you explain again?
You understand determinant, right?
Yeah.
Determinant is just some number. That is determinant. So, determinant, if you have upper triangular matrix, determinant value equal to multiplication of the diagonal term. Lower triangular matrix, determinant is multiplication of the diagonal term. Diagonal term of matrix L is just 1.
Yeah.
Okay, so this term become 1. That's how you get this.
Okay.
But you have to worry about S. S is the number of times that switching occur. If you switch row and column, switch two rows together, then determinant change by minus 1. I mean multiply by minus 1. So what I do is, when I switch, I don't just switch P, I don't just switch A, I also count the number of times that I switch. So I start with S equal to 0 and I count how many times I switch. Okay, this way I can calculate determinant easily. So when I calculate determinant, I use NP dot product. Okay, you answer range N, range N. What's that? This means it's a zip between 0, 0, 1, 1, 2, 2, 3, 3, 4, 4, 5, 5, or NN, just diagonal term. So the index here, I put range as an index. So that tell you the diagonal term.
Can't you just put
If
it
you
like,
don't, how do you can do this or do this? It's the same. That's my point. And if you don't feel comfortable of this, take it out and type it down and find out what happened by yourself. Okay? So UII is a product of the diagonal term. You can do for loop for that. And determinant is minus 1 to the power of s multiplied by UII. Done. Return determinant. Okay. So I try to calculate this part. I show you how I debug the program, how each part works. You see this one? A range 5, range 5. It gives me just a diagonal term. You see? So this is how I know type that will work. Okay. Let's take a look at the result. My method give me 1316 something. This method, linear algebra.det, give me the same thing. So my method work. Doesn't mean it's faster. If my method work, my work is done. Your work is going to start by take a look at it and understand the algorithm. Okay? That's your work. So now I show you how we can calculate determinant and it gives the same number. What about the speed? Of course, my way is 20 times, 10 times slower. I don't care, but at least you know the algorithm. It gives the same answer. Okay. If you do LU decomposition, you can get depth of each of them and multiply them to each other. If you use PLU of SciPy algorithm, it doesn't return S. You don't actually know how many times that switching happened. So the automatic function doesn't return you like S. So what do you do? So this time I try to show you how do we get the determinant of matrix P. Basically this function is to do that check. Okay, and is it okay? If you look at it carefully, you see this line, that P, new P. Then underscore P, so this is my own function, okay, by the way. So this is my own function, which is the name that P. Okay? The return of my function is the call to the same function. So this is recursive. Why do I write it as recursive? Because just in this case it's kind of easier. So that's why I write it in recursive format. Recursive format means it calls itself infinity time until it reaches the starting point, then it calculates back, put this all number together and it's done. Just be aware of this, may not be enough, but you should go over it and find out how it works. In every recursive function, you have two main components. Component number one is the exit condition. Component number two is recursive condition. So exit condition is over here. If n equal to 1, return 1. That's the exit condition. Otherwise, update the calling argument and call it again. So you see this new P? New P is actually smaller than the original matrix. If you put matrix P in, it deletes some row, deletes some column, and it becomes a new argument. So this means you delete one row, delete one column, delete and call. Once you call, you delete again, and then you call. Once you call, you delete again, you delete row and you delete column. This is from the principle, right? The formula to calculate determinant is if you look at the lecture in the presentation file, you delete one row, delete one column, and then you multiply by determinant of smaller matrix. And then you keep doing that until you do it every row. See my point? So this is equivalent to that. Delete one row, delete one column, calculate determinant. When I calculate determinant, I keep deleting until I cannot delete anymore. If it's one by one, I cannot delete anything. If I delete it, it's crash, right? So I delete it until I don't have anything to delete. That's what it is. You will go over it in the homework. Okay? How do you know how it do the calculation? You put a print statement over here. Maybe on this line, you put some kind of print statement. So this way it print every time that it do the recursion. Okay? That's how you know. And hopefully when you know this, I don't teach you how to write it, but you see it's not that complicated. Then hopefully you can write it for yourself too.
What does this again?
Recursion.
S type.
It is to calculate determinant. If you remember, determinant equal to what? A11 multiplied by, or A00 multiplied by determinant of subset of A after you delete row 0 and row 1 plus something else. But for matrix P, you don't have to do that for every column because only one of them is 1, the rest is 0. Check the homework. Okay, that is determinant of matrix P. So this way, I test it and it worked. It gives the same answer as psi pi. So it's correct. So this is determinant without S. So I get that of P multiplied by the product of U. So I'm done. So you can get the determinant of permutation matrix too. If you have permutation matrix, you call my function, then it gives you the determinant. Okay? The code is there and just need you to look at it. So we are done with that. Gauss-Jordan. I still have 2 minutes. Gauss-Jordan matrix inversion. Okay, the formula is, this formula is exactly the same as what you have in Gaussian elimination, isn't it? But you do Gaussian elimination twice. First time, you append identity matrix to the right hand side. You see this identity matrix on the right hand side. On the left hand side is your original matrix. Then you do Gaussian elimination. Okay, you eliminate this term, you keep eliminating twice. Once you finish the first round of elimination, get 0, 0, 0, 0, 0, 0. So first round of elimination, everything on the bottom left triangle becomes 0. Of course, you will get something update on the right hand side. Okay, that's the first round. Second round, you delete this top right. Then the right hand side, whatever you get, that's the inverse. Okay, you did it again. That's the inverse. Your job is go check the code. What did I do to make that happen? And you know enough to do that already. Last one, I think I put everything together and I make Gaussian Jacobian. So to do matrix inversion. That's it. We are done with matrix inversion. Go check the code. Thank you for coming.
Can you show us how to do the SOR thing?
Oh, SOR. Okay. Sorry for the extra time. SOR, last time I made it, but it's have the error because I didn't do it correctly. It's have error. Now I have answer. I use M inverse to get the answer. I get the answer, I put the answer in, and then everything become correct. What I did is like last time, you remember, I split to be D and R. R is the rest, right? And D. Then I calculate, so this is matrix A, input matrix. That's matrix A.
Professor, there was the input matrix had some problem. There was some in the upper triangle matrix. There was
Something-
minus four there. Yeah,
Oh, you put it there?
it's not 0. It's minus 4 there, and
Yeah, you put it there when you do the homework.
yeah, I did that.
And it's just fine.
Yes, this
So-
gave me the same thing.
Okay, so my code is work. It work, right?
Yeah.
It works. So when you do it, you put minus 4 and minus 4 over there. So here is what? Matrix D, diagonal term. Everything set to diagonal except that is a link to the diagonal term. And R is the rest. 1 over D is over there. It's 1 over the diagonal term. R multiplied by X, I use M out. Okay. Then I do B minus RX. Then I do D minus 1 or D inverse multiplied by B minus RX. First time I did it, I have error. And I don't know what's error. So what I did, after some of you left, so what I did is, I get the answer, I put the answer in, use M inverse, and I get the answer. And I put the answer in as the initial guess. So initial guess, instead of 1, 1, 1, I put initial guess as the answer, and I check where's the error. And then I managed to fix it. I forget to put the $ symbol or something. So once you finish this row, you copy and paste several times. Then you don't have to do that. I did it for you already. Okay. So your task is for SOR and something else. For SOR is more than D and R, right? It have something else too. Keep doing it.
The
This
problem
is
was that the inverse of the matrix, if you do it this way, if you put an M inverse, and if you just go to element by element and inverse it, it doesn't give the same answer.
you have to highlight the whole thing.
Yeah, you have to invert.
You have to do the whole thing, not just element by element.
The M inverse will work, but if you go element by element, divide 1 divided by this, 1 divided by this, it doesn't give the same
Unless
answer.
your matrix is diagonal.
Yeah, unless the method right.
You see, this one I use 1 over something, 1 over something, 1 over something. It works only for the case where your matrix is a diagonal matrix. For the diagonal matrix, the inverse of the diagonal matrix is 1 over the diagonal term.
Mm-hmm.
What's that? Okay, it's 5 minutes more, sorry about that. For more help, come to see me today, tomorrow, it doesn't matter. See you next time, and next time we will try to cover everything quick.
Thank you,
Bye-bye.
sir.